Yes friends, welcome once again to the class, and today we are going to learn about nuclear decay. Okay, so let us start a new topic of ours, which is nuclear decay. And in this new topic, nuclear decay, we are going to learn about three type of decays: alpha decay, beta decay and gamma decay. Okay, so we are going to learn about alpha decay, beta decay and gamma decay in upcoming classes, and we are today starting with alpha decay, by the way. Okay, so nuclear decay topic has been started by our YouTube channel. Okay, and already 40 lectures have been done. Okay, as far as nuclear and particle physics of UPSC CSE physics optional is concerned. Okay, as far as nuclear and particle physics chapter is concerned, already 40 lectures have been done. Okay, so you can watch the previous 40 lectures by going to the link in the description, and from there you can watch from the very first lecture. You will understand each and every concept very clearly, because I have taught everything very clearly without any prior knowledge required. Okay, without any prior knowledge required. So you can certainly go to the link in the description and start from the very first lecture. So you will understand each and everything very clearly. Already 40 lectures have been done, and this is lecture number 41, by the way. Okay, so the stable nuclides have definite Z and N combination. So now, what does it mean by stable nuclides? Stable nuclides means those who do not undergo any, the nuclides which do not undergo any decay. Okay, those are stable. Okay, what are stable nuclides? Stable nuclides are such nuclides which do not undergo any type of decay. They do not undergo alpha decay, they do not undergo beta decay, they do not undergo gamma decay. Okay, so such nuclides are what? They are stable nuclides. Okay, sometimes stable nuclides have very high value of half-life. Okay, for example, some of the nuclides have a half-life of 10 to the power 33 years. Okay, so if a nuclide has half-life of 10 to the power 33 years, it means that that particular nuclide will remain in the universe even after means its half-life is even greater than the life of universe. Okay, so some of the nuclides are there whose half-life, I have already told you what does it mean by half-life. I have already told you what does it mean by half-life. Okay, so the meaning of half-life I have already told you. So according to that definition, if you look at the half-life of certain nuclides, okay, so let me write over here, half-life of certain nuclides is even greater than life of the universe. So half-life of certain nuclides is even greater than the half-life of the universe. So such nuclides also come in the category, okay, in the category of stable nuclides. So they also come in the category of stable nuclides. Okay, half-life of certain nuclides is even greater than the life of the universe. Such nuclides also come in the category of stable nuclides. Okay, and some of the nuclides have half-life even infinity. Okay, some of the stable nuclides have half-life of infinity. Infinity half-life means that they do not decay. What does it mean by infinity half-life? Infinity half-life means they do not decay. Okay, certain nuclides are there which do not decay, and some nuclides are there which decay, but their half life is even greater than the life of universe. So such nuclides also come in the category of stable nuclides. Okay, so let us see. The stable nuclides have definite Z and N combinations. Now, what does it mean by Z? Z means atomic number. What does it mean by N? N means number of neutrons. Okay, Z means atomic number, that is number of protons. Okay, so Z is what? Z is number of protons, which is atomic number. I have already told you. And what is N? N is your number of neutrons. Okay, so those which are stable nuclides, they have definite Z and N combinations. Okay, so they have definite number of protons, they have definite number of neutrons. Okay, in their nuclear shells. Okay, in their nuclear shells, definite number of protons and definite number of neutrons are there. So definite Z and N combinations. Okay, definite Z and N combinations. So some of the combinations of Z and N, some of the combinations of Z and N, they are stable, and some of the combinations of Z and N, they are unstable. That depends on the nuclear configuration. Okay, that depends on the nuclear configuration. In which subshell, in which nuclear subshell the last nucleon is going. Okay, in which subshell the last nucleon is going. According to that, the stability will be defined. The stability will depend on all those factors. Okay. Now, nuclides with other Z and N combinations are also found in nature. Okay, so other than stable nuclides, some other nuclides might be found which have other Z and N combinations. So they are also found in nature. Okay, other Z and N combinations nuclides are also found in nature. For example, if we take the example of oxygen, so O816 is one oxygen combination. This is one combination of Z and N. So this combination of Z and N is Z equal to 8 and N equal to 8. This is the combination, right? This is the combination. Then other combination which we have with us is O817, and in this particular case Z is 8 and N is what? N is 9. Okay, then we have one more combination, right? One more combination of Z and N, one more combination of Z and N, which is O815. Okay, so in this particular case Z is 8 and N is what? N is 7, right? So in this case Z is 8 and N is 7. You have clearly seen this. Okay. Now let us erase all this stuff. So nuclides with other Z and N combinations are also found in nature or may be prepared in the lab. So they are either found in nature or may be prepared in the lab. In the laboratory also, trans-uranium elements, okay, the nuclei of trans-uranium elements. What is the atomic number of uranium? Atomic number of uranium is 92. Okay, atomic number of uranium is 92. And the nuclides which have been prepared after uranium, okay, the nuclides which have been prepared after uranium, for example neptunium, plutonium, okay, and the further ahead of those are what? Those are artificially prepared nuclides. Those are artificially prepared nuclides, and those nuclides are prepared in the laboratory. Those are man-made. Okay, those are man-made. So those are man-made. Now man-made nuclides are also there. Amongst the lower nuclides also, some of the nuclides you can prepare in the lab. Okay, some of the nuclides, for example technetium. Okay, for example atomic number 43 technetium, it does not exist in nature. Atomic number 43 technetium does not exist in nature. So we prepare that in the lab. Okay, so nuclides with other Z and N combinations are also found in nature or may be prepared in the lab. Okay, so they might be prepared in the lab as well. Now if you talk about some of the elements, for example francium, if you talk about francium, Then what is the speciality of francium? The speciality of francium is that if you dig the entire earth, okay, if you dig the entire planet earth, if you actually take out all the francium, okay, if you take out all the francium from the planet earth, okay, if you take out entire francium which is present on planet earth, if you extract entire francium from planet earth, what happens? If you extract entire francium from planet earth, you will hardly get 1 kg of francium, okay, you will hardly get 1 kg of francium on entire earth, okay. So there is only 1 kg of francium on entire earth. There is only 1 kg of francium on entire earth. So only 1 kg of francium is there on entire earth. So very rare element indeed. So it is what? It is very rare element, okay. Or may be prepared in the lab. These nuclides are unstable and decay into other nuclides by various processes. So these nuclides are what? They are unstable. These rare nuclides are what? They are unstable. These man-made nuclides and rare nuclides, these are unstable, and they decay into other nuclides by various processes. So they decay into other nuclides by various processes, okay. So we have two main processes with us. They decay into other nuclides by various processes, and we have two main processes existing, that is alpha decay and beta decay. And gamma decay also occurs sometimes, okay, but gamma decay does not change the number of protons and number of neutrons, okay. I have already told you the concept of nuclear isomerism. Nuclear isomerism concept I have already told you. Whenever gamma decay occurs, it does not change the number of protons and number of neutrons. Whenever gamma decay occurs, it does not change the number of protons and number of neutrons in the nucleus. It just changes the excited state, okay. It just changes the state of the nucleons. What happens in gamma decay? In gamma decay, only the nuclear configuration is changed. In gamma decay, only the nuclear configuration is changed, but the number of protons and number of neutrons do not change in gamma decay, okay. As far as alpha decay and beta decay are concerned, number of protons and number of neutrons change in alpha decay and beta decay, okay. In alpha decay and beta decay, number of protons and number of neutrons change after the decay. Number of protons and number of neutrons change after the decay in alpha decay and beta decay. But in gamma decay, there is no change in number of protons and number of neutrons, okay. There is no change in number of protons and number of neutrons in gamma decay, okay. Only nuclear configuration changes in gamma decay. Only nuclear configuration changes in gamma decay, okay. So that is the thing. So the stable nuclides are definitely, these all are done. These nuclides are unstable, decay into other nuclides by various processes. Two main processes are alpha decay and beta decay, already learned, right? Two main processes are what? Alpha decay and beta decay. Now when n by z ratio, when number of neutron is to number of proton ratio, when what does it mean by n? N means number of neutrons. What does it mean by z? Z means number of protons. So when number of neutron is to number of proton ratio, it is less than or equal to 1.5. Okay, when number of neutron is to number of proton ratio, it is less than or equal to 1.5. Then such a nucleus is what? It is a stable nucleus. When number of neutron is to number of proton ratio, it is smaller than or equal to 1.5. Then it is stable nucleus. Usually I am saying, okay, this is not hard and fast rule. This is not hard and fast rule. It is usually seen that the nuclides which have n by z ratio smaller than equal to 1.5. Okay, the nuclides which have n by z ratio smaller than or equal to 1.5, they are usually stable. Okay, not hard and fast rule. There are many exceptions. To this rule, but this is not hard and fast rule. But usually it is seen that n by z ratio smaller than or equal to 1.5 is stable. and n by z ratio greater than 1.5 is unstable. Okay, again not a hard and fast rule. N by z ratio greater than 1.5 is unstable. This is also usually seen, but not a hard and fast rule. Again not a hard and fast rule. Okay, so these are the things. Gamma decay also occurs, but in this process no new nuclides are formed. Okay, so in gamma decay the identity of the nucleus does not change. What does it mean by gamma decay? In gamma decay the identity of the nucleus does not change, that is the number of protons and number of neutrons do not change in gamma decay. Okay, so a nucleus simply transits from higher energy state to lower energy state, emitting a gamma photon. So the nucleus simply transits, that is nuclear configuration changes. Okay, what does it mean by nucleus simply transits from higher energy state to lower energy state? What does it mean by that? It means that in the higher nuclear shell, if a particular nucleon is the higher energy state, it will transit to the lower energy state, thus emitting a gamma photon. Okay, this is the meaning of that. So gamma decay also occurs, but in this process no new nuclides are formed. So in this particular process no new nuclides are formed. A nucleus simply transits from higher energy state to lower energy state, thus emitting a gamma photon. So it will emit a gamma photon and it will just transit from higher energy state to lower energy state. Okay, and the number of protons and number of neutrons will remain unchanged. Unaltered or unchanged. Now let us understand what is the alpha decay. But we will learn about the alpha decay in the next class. Okay, Thank you very much. Jai Hind, Jai Bharat. Please like, subscribe and share our videos, and please give the videos a very big thumbs up, so that the hard work is so that I feel motivated to do the hard work. Just give the video a big thumbs up so that I remain motivated to do the hard work for all you people, all of you guys. Okay, so thank you very much.